Hello and welcome to Team VLSI. Today we are going to discuss clock skew in the fringe of STA concepts. If you find this video is relevant to you, please like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can search Team VLSI on Google. First of all, highlights of this session. This session is going to very short, and we are going to discuss in this session clock skew, including positive skew and negative skew. We'll also discuss local and global skew. So let's begin. What is clock skew? And to explain this, I would like to take this simple example. Suppose this is your block, and there are millions of flops sitting inside your block. I have taken only 3 here for example, and to operate these flops, there must be a clock going to these flops. There could be more than one clocks in your block, but for simplicity, here I am considering a single clock which is being distributed to all the flops. So how your clock is distributed inside your block? Obvious, there are some clock distribution system. It could be either H tree, your mesh, or any other clock distribution methods. Clock will distributed from this clock definition pin to all the flops, right? Clock skew. Clock skew could be defined as the difference of arrival time of clock edge in 2 sequential elements. So what I'm saying it is the difference of clock arrival time, means edge of clock edge arrival time in 2 different sequential element, right? That's our clock skew, or we can define it is the difference of latency of 2 sequential element. Suppose this flip flop 1 has latency L1, means network latency, that is the delay of clock to propagate from the clock definition point to the CK pin of this flip flop 1, that is L1, and the clock latency for flip flop 2 is L2, and there exists a data path from flip flop 1 to flip flop 2. Then we can define the clock skew is equal to latency of capture flop minus latency of launch flop, right? For clock skew, here clock skew is L2 minus L1. Clock skew is mainly because of difference in length of clock path and amount of buffer or inverter added in the clock tree, right? Ideally, 0 skew is expected after CTS. If the clock tree is ideal for the latency of all the flops would be equal, ideally it would be 0, but in practical it is not possible. For we provide a constraint of maximum skew when we built the clock tree, that is in the clock tree specification file, we provide the maximum skew. Okay, right. Now we'll see a positive and negative clock skew. Suppose this is a clock definition point, and clock is being distributed in these flops, and there is a data path between them. If there is a timing path between 2 synchronous element, then clock skew can be defined as clock skew equal to clock latency at capture flop minus clock latency of the launch flop, as we have discussed in the previous slide. Clock skew could be either positive or negative or 0, right? Let's see the positive skew. Suppose if L1 here, that is the latency of launch flop, is lesser than the L2, flip flop 1 will see the clock first, then flip flop 2 will see the same clock after some time, after some delay. Here clock latency is arrival time of clock at flip-flop 2 minus arrival time of clock at flip-flop 1, and obviously it is positive here since L2 is greater than L1, so this is the positive skew. So positive skew can be defined as a capture flop latency is, for in case of positive skew, capture flop latency is greater than launch flop latency, right? And in case of negative skew, suppose L1 latency of launch flop is greater than L2, then what will happen? Launch flop will see a delayed clock with respect to the captured flop. So capture at the capture flop, clock will arrive first with respect to launch flop. So in this case, this skew will be negative since our L1 is always lesser than L2, right? So in case of negative skew, capture flop latency is lesser than launch flop latency, right? So I have a question here for my audience that which type of skew is helpful for fixing setup and hold. So you can comment your answer in the comment section. I want to ask that only either negative skew will helpful to the setup or positive skew for the setup, or and same case for the hold. Which type of skew will be helpful to fix the hold, right? So next we will see the global and local skew. So we have seen this diagram before. So local skew can be defined as the difference in clock arrival time of two related flops is called local skew, right? And global skew is the difference of maximum latency and minimum latency in the design between two non-related flops, right? So global skew is always the match skew, and it is not necessary that those two flops have a data path. Means it could be non-related or related. For the maximum differences of latency inside your block is called your global skew, right? And at last, we all know that in case of pre-CTS stage, there is ideal clock. So we include the expected skew in clock uncertainty. Okay, but after CTS, clock tree is built and exact network latency get calculated. So we have exact skew value. So pre-CTS we have not skew there. So but there is expected skew that we have included in our uncertainty factors. And after CTS, our clock tree is built and routed. So exact skew is calculated after means post CTS. Okay, so we can reduce our uncertainty. We can actually reduce the skew factor from the uncertainty, and that's why generally post CTS uncertainty is lesser than pre CTS latency, right? So with this, I would like to conclude this session here. Thank you for watching this session. If you find this session is relevant to you, like this video and subscribe our channel. You can also share this video with your friends and colleagues. So now you can also visit our blog, that is teamvlsi.com, or you can visit our FB page also. You can join our WhatsApp and Telegram group. The links are given in the description of this video. Thank you for watching this session.